button and maybe it works. Yeah, great. All right. We'll see how long that works for. So which of the following is highest energy? Ultraviolet, infrared, visible microwaves. This could be reworded as what is the most dangerous? The same thing. Out of these four, there's, I did not put the one with the highest energy on here. All right, we'll go to 140. It's a pretty straightforward, no math required kind of question. There is one question in the problem set that says, what category of waves is this? I just put that in there just because it's interesting. Again, I'm not going to test you all. That will never come up with a test. Stop it in 3, 2, 1. So you cannot expect anywhere on the test or the quiz for me to ask that kind of question. So don't worry about it. Yay, ultraviolet. Yay, good job, us. Most energy, not dangerous necessarily, but long time. You know, you've seen stuff. You're heard stuff. All right. This is the one. This is the only question, and the answer is kind of right there. If you wish to detect details of the size of atoms about 0.2 nanometers with electromagnetic radiation, it must have a wavelength of about this size. What is its frequency, and what type of electromagnetic radiation might this be? So this problem is really interesting because it turns out there's a limit to what optical microscopes can view, because there is things smaller than the wavelength of light. The wavelength of light, the smallest it gets is about 400 nanometers. If you are smaller than 400 nanometers, it cannot pick it up. It cannot image it. It's kind of like if you put your finger and you wanted to feel the surface of something and there was a hole that was like a millimeter, you're barely going to be able to pick up that hole. You're not going to be able to pick up much detail on it. Your finger can't detect the size of atoms on this table because your finger is bigger than atoms by a long shot. This is the same idea. Optical microscopes have a limit. There is equipment that can view the size of atoms. They're called scanning tunneling microscopes, or AFMs is another one, and they use different mechanisms. But anyway, this is also, well, there's one more type here. This is, I'll start answering the question and I'll describe it more as we go. So its size is 0.2 nanometers, which means, how do we approach this problem? I need a wave with roughly this size or smaller. A smaller wave is fine, but I can't have a wave that's bigger than this and get good resolution. As it says here, it must have a wavelength of this size. So, there you go. That's all it's given. What's its frequency? F equals mystery. What equation are we going to use? Give you all a few seconds to think. I've only given you one variable in this problem. Yeah, sure. If you have a guess for it, go for it. Yeah, C equals lambda F. We're going to solve for frequency here. We know C. And so now it's just plug and chug. C is 3 times 10 to the 8. It's a handy number to know. It's not too bad to remember. If I can remember it, that's a pretty good sign. All right, and it's old plug and chug. 3e to the 8 divided by 0.2e to the minus 9. And we get a frequency that is very big. (1.5 times 10 to the 18 hertz. Very, very large. And if we look at our little table here, and we look at, what was our power? 10 to the 18? 10 to the 18 is, oh, look at that, it's nicely labeled, and we're at X-rays. This is actually used in, oh, I forget the name of it. X-ray diffraction. The X-rays can be used to determine the lattice structure of crystals. So you can have a crystal, you can use X-rays, and it'll actually kind of go in between them, and you can get you can actually determine the pattern of various crystals. And when I use the word crystals, we're not talking just, diamonds and sapphires and stuff like that. Crystals, silicon that's in your phone is a crystal. A crystalline structure is just a repeating pattern. Lots of things have it. So there you go, that's a quick answer, not too bad. I'm not going to ask part B on the test or anything like that. Part A is totally free game, super easy problem for you all. Should be no problem. All right, so now we're getting into the two things I want to talk about today, which is reflection, the two big ones that is going to kind of come up, reflection and refraction. Bouncing off of things and bending through things. Reflection should be super simple. If you know what a bouncy ball does, you know what light does. Light bounces like a bouncy ball. Light reflects off of surface, and then it says it bends this. We're going to imagine light as a ray, which is a straight line, just because it makes our diagrams easier. We're not going to be drawing waves like this because it offers little benefit. We're going to just use these straight arrows, imagining that almost like a laser beam coming through, and it will describe how light behaves. So this is pretty traditional notation. So getting into the bouncy part, light bounces off at the same angle it hits with, just like a bouncy ball. If you bounce it straight, now this depends on the surface. If the surface is nice and smooth, it's going to bounce with that. This also does apply to bumpy surfaces, and I'll describe that in a second. But for now, when light hits a surface, it's going to bounce off at the same angle it hit with. Where do we measure that angle to? We measure it with respect to the area vector. Good old area vector. Remember, the area vector is if you have a flat surface, it is the one perpendicular to the surface. So basically, take your pen or pencil, put your eraser flat on your surface, and ta-da, you have generated the area vector. You can apply this to any problem. Say I have a circle, and you want to know the area vector at this point. Literally take your pencil or pen and put the eraser flat on that so that the eraser is as flat on that surface as possible. Ta-da, there's your area vector. Oh, you want to know the area vector over here? Put your pen flat on it. Oh, it's that way. You want to know it up here? Area is that way. It is the vector that is perpendicular to the surface. The surface in this case is that way. That it changes on a sphere, but you can use that nice little trick of just take your pencil, put the eraser flat on it, and it will point in the right direction. And you can see here, if I threw a bouncy ball this way, it's going to bounce this way. Light does the exact same thing. If it comes in with 30 degrees, it bounces off at 30 degrees. If it comes in with 40 degrees, it bounces off at 40 degrees. Just like a bouncy ball. So, what happens when our surface is bumpy? The same rule applies. If you look real careful, there's these little dotted lines, and these are my area vectors. So here, I put like my pencil here, and the area vector is here. Here, the area vector is here. Here, the area vector is here. And you can see, you'll have to maybe look at these slides later if you want to see it in detail. It's kind of hard to see. The angle it's bouncing off is the same. Why is it bouncing off in a bunch of different directions? Because the area vectors are in a bunch of different directions. This is why mirrors are shiny and wood is not. Wood is bumpy. The light comes in, and the surface it hits, it's all bumpy. There's all these different area vectors. So which way it bounces off, it's still behaving like a bouncy ball. Think of a bouncy ball. If I bounce a bouncy ball on a hard, concrete, smooth surface, it's going to do nice things. It's going to be predictable. If I go on a gravel road and I bounce a bouncy ball, it's going to not be as predictable because it's bumpy and those area vectors are all over the place. And so it's the exact same, that's the rationale. Yeah?
If we have a textured surface like a problem, is it okay to assume that wherever the light hits will always be perpendicular, like to like a very specific tiny point?
The key to that, let's just make up some problems real quick. Let's see, is the next one made up based on this? Nah, that's not good enough. Let me just make up a picture. If, say I have a bump, and I say light is coming in like this, and I say find which way it'll bounce off this point. Take your pen, I'm going to even draw it. Imagine you took your pencil and you put it flat here. I'm going to draw a pencil, because there you go, it's red. I don't know if pencils are red. Let's make it, there we go, there's my pencil. I put my pencil flat on that surface. It's going to bounce off with the same angle it came in with. So that's the key to doing this. Draw that pencil, draw that area vector, and then just draw a line on the other side that's symmetric about it. Yep. And you can do that with any point to determine which way it will go. So, hopefully that helps. Now, if light hits a mirror at a 30-degree angle, this angle is measured with respect to the normal. That's the one that we just been talking about. What will be the reflected angle? The reason mirrors are so shiny is they have a silver surface, and that silver deposits when they make it. They deposit it very smoothly. You can basically make anything a mirror, though, if you just shined it enough. If you make that surface smooth enough, it'll turn into a mirror. Mirrors are just cheaper to make than taking a piece of wood and polishing it a bunch. You polish a piece of wood enough, it gets shiny because you smooth the surface. Everything that's shiny is just smooth. Everything that's not shiny is not smooth on some level. Bricks aren't very shiny. They're very rough. Most metal is shiny. They're pretty smooth. So if you took some sandpaper to the metal, now it's not. Because it's rough. All right, we will go to 125. Now, getting things super smooth, like the James Webb Telescope, that's a whole process in and of itself. Polishing something for like laboratory grade equipment, that's challenging. 5, 4, 3, 2, 1. Fingers crossed. I'm hoping this turned out really well. It is 30 degrees. Which, it's okay that people miss this. So the incident angle is measured with respect to this normal. So if I draw a picture, if it comes in with 30 degrees, this incident angle is angle with respect to this normal. It bounces off with 30. I'm not going to try to trick you all. I'm not going to try to give you a problem where I say 60 degrees with respect to the surface or anything like that. These problems will be this obvious. Basically, I just want you to know the angle it comes in with is the angle it leaves with. That's the learning objective here, so I'm not going to try to trick you with anything weird. All right, so what makes something shiny? We already talked about that. The smooth and dull, it's another thing that shows the exact same thing. All right, great. This is a fun question. This one requires some thought. Not going to be on the test, so don't worry about this. But it's a fun question. It's worth talking about. It's worth the time. If I'm 3 meters tall, what is the smallest size mirror I need to see my entire body? Is it a full-size mirror the size of your entire body? Is it a mirror that's half the size of your body? Is it a mirror that's 1/6 the size of your body? Or will any size mirror work? Tiny little thing. If I look in my room, yeah. And we're assuming a flat surface. That's really important to clarify here. The mirror I'm talking about is a flat surface. We're not talking about a curved surface because that changes the situation. We're talking about a flat mirror. Let me even put that here. What is the smallest size flat mirror I need to see my entire body? Because if the mirror is curved, it changes the whole problem. All right, we'll go to 130 for this. Five, 4, 3, 2, 1. All right, so the key to this problem is drawing a picture. There I am in all my glory. And let's just imagine I had a full-size mirror. That's kind of the extreme. Let's imagine I had a mirror the size of my whole body. We would hope that I'd be able to see myself in a full-size mirror. Let's see if we need the full size. The trick to this is think about what is the things farthest from my eyes. The eyes are what's going to see everything. So what is farthest from those? That's my feet. My feet are the farthest thing from me. They're going to have to travel the farthest distance-wise to get to my eye. And let's think about what would happen. They need to get up here. So they're going to go. They're going to bounce right off the middle. Because when you see something, you are seeing the light that is transmitted off it, and it has to get to your eyeball. If I pick my kneecap, let's draw that ray. Something like that, something symmetric. If I draw the middle of my body, something like that. If I have right where my eyeball is, I need something that'll go straight there and straight back. Long story short, you don't need the bottom of the mirror. You all can test this for yourself if you want. Go find some mirrors, see if you can see your whole body if it's really tiny. Even distance doesn't matter. I picked an arbitrary distance. This rule will apply no matter how big or small the mirror is. You need a mirror half the size of your body to be able to see your entire body based on the law of reflection. Again, go test it for yourself. Now, you may think, I have those little handheld mirrors and they can see a lot. They're curved. If they're curved, they can... If I have a curved mirror like this, then the light's going to bounce differently than it will on a flat mirror. And you can look into that kind of on your own. I won't spend really much time on that. But this is just a fun little thing to kind of show that if you know the rules, you only need a mirror half the size. Interesting. I'm not going to test you on it, so don't worry. But, take that to your next wine and cheese party or whatever. Ask people that. Then you can draw a picture, and then they'll be bored halfway through, and I don't know. Whatever. Another kind of fun question. This one doesn't have a clicker question. How can I design something to make a wave always bounce back in the same direction it came from? So I have some magical object, I'll make it all squiggly, that if a light ray comes in, it goes back the same way. No matter which way it comes in, it comes back in the exact same direction that it goes from. Who cares what direction? Yeah, sure, go to guess. Curved one? So concave, we're not going to learn about mirrors too much in terms of the concave ones. Those ones, if light comes in, it may, but it depends upon the angle. It depends. It's a very specific angle. The solution to this is fairly simple. It's kind of like that, but it is two mirrors at a 90-degree angle from each other. Two pieces of whatever at a 90-degree angle. And now this is how reflectors work. When you all like how that reflector you see do at nighttime and you shine a light at it and it bounces right back at you. It is literally, if you look at it closely, just a bunch of things at a 90-degree angle to each other. You can test this for yourself. You can draw any arbitrary line, do the whole bouncing thing, so it bounces with the same angle it comes with. It's going to hit this one. It's going to bounce. I mean, I kind of just drew this. Let me draw a crazier one that's not identical to that. That one did work, but it was already on there, so it wasn't very interesting. So you have a wave coming in at a really steep angle. We draw our normal. It's going to bounce off with the, make sure my drawing is good so that I don't lie to you. It's going to bounce off like that. We draw our area. So this angle and this angle are identical. This angle and, no, that's not very pretty. Okay, my drawing's not perfect. Oh, actually, that's not bad. I just didn't draw my area vector very good. If you draw these lines really straight, you can see that any lines you draw will bounce right back where they came from. Very useful for if you're on the road, you don't know where the car is that's coming at you. You don't know where the headlights, some headlights are higher, some headlights are lower. Are they coming at you this way, this way, this way? No matter what angle they come at you with, the light will bounce directly back. What else is this useful for? These are on boats. If you want to know the location of a boat out in the ocean, if you send out like a radar thing, that radar is a form of light. It's going to bounce, return right back to the radar station, give you the exact distance by just when did the ping go out, when did it come back, you can time it. They have one of these on the moon. They shine a light, there's a reflector that they placed on the moon when they went to the moon, and because of this, they can shine a light right at this thing, time how long it takes for that light to come back, because it will come directly back, and they can see how far away the moon is, precisely. So, these are used all over the place, and they're just two things at a right angle. You may look at this reflector here and say, that's not very shiny. That's because it's not reflecting visible light, it's reflecting radio waves, which don't care, they care about different things. So, anyway, fun facts galore. All right, okay. Reflection, done. Reflection is easy. Light bounces at the same angle it hits with, no problem. Refraction, light bending. This is what explains why when you look into water, you all have seen like the pencil that looks bent in a cup of water. You've probably seen that at some point. You know, if not, Through the power of Google, we'll pull up a million pictures of it. Refraction, pencil and water. You know, it's one of the, look at all these beautiful pencils. Wow, they're all bent, they're all broken. No, this will explain why pencils look broken or any other object looks bent when it's in water or really any medium. This is something you all have seen, maybe not realized, maybe have. The reason is, I keep telling you light travels at the same speed. From light's perspective, it travels at the same speed everywhere. But if you're kind of out here, light does slow down when it enters water or really anything other than vacuum. And so towards that end, when it slows down, you can imagine light as we're going to kind of draw these lines as like a marching band. And say a marching band is walking on, there's a good video here, I'm going to let you check it out in your own time. I'm not going to play it for you all, but feel free to go and look at it. It does a really good job of animating and showing it, not the timestamp in particular, what it shows. But as that light hits, you can almost think of like a marching band hitting some mud. And these people that hit the mud, they're going to start walking slower. These people on this side, they're going to start walking slower, whereas the rest of these people are going to be walking just as fast. So these people are going to travel less distance in the same amount of time. And so this light will start to bend because of this change in speed. These people will be going slower. These people will be going the same speed. And so you get this bending. The original rays are all kind of parallel to each other still. Let's pull up this quick animation. It's going to draw, hopefully works. And it'll do a better job kind of showing it. So these light rays are coming in. The second they hit the medium, they slow, but these ones still have to stay parallel to each other, and they have to still be traveling at a quick speed, and the consequence is the whole light ray bends. The video I posted does a great job of kind of showing this and explaining this better than I can because it uses a lot of visuals and stuff like that. You don't need to exactly know all the mechanism. That's just kind of if you're interested conceptually. You do need to know, though, that light bends when it passes through material, and it slows down when it does get to denser materials. Okay? You don't need to exactly know the mechanisms why, but just know that it does. And so towards that end, we have this equation, N equals C over V. It's called the index of refraction. Every material has an index of refraction, assuming light can actually pass through it, which most materials can. Metals are a little funky. There's no units for this. It is a ratio. It is a ratio of the speed of light to the velocity in that material. And because it's a ratio, the units for C are meters per second. The units for velocity are meters per second. If you do meters per second divided by meters per second, there's no units. It's a ratio. It's basically how much slower does light travel in that material compared to in a vacuum at its maximum speed. So in vacuum, it's all traveling 3 times into the A regardless of its frequency, regardless of this. And this rule here does not depend upon wavelength or frequency. They all, no matter the frequency, no matter the wavelength, they all get slowed down the same amount. A radio wave and a gamma wave will travel at the same speed in the same material, and it will seem to be slower. Fairly simple equation. C is 3 times 10 to the 8, N will be a number, V will be a number. I'll give you 2 out of those 3 things. I'll give you 1 of them. You get C. All right, so thinking of that equation, I want you all to think about, I have water with N equals 1.33, and I have glass where N equals 1.5. What is light traveling faster than? Which one has the higher V? Is it water or glass or not? go to 130. Five, 4, 3, 2, 1. All right. So there's two ways you can think about it: mathematically and conceptually. Conceptually, light travels the fastest in vacuum, which means nothing, absolute nothing. So basically, the more dense we get, the slower it's going to get. If it travels the fastest when there's nothing, it's going to get slower as the material gets denser. Because vacuum is as least dense as possible. It's absolutely nothing. So, you can just look at these and say, which one's more dense? Water or glass? In this case, it'll be glass. Glass is more dense than water. You don't need to know that, though, because we have equations. Our equation says that N equals C over V. And so the question, C is a constant. Let's just put that number here. 3e to the 8 over V. So the question is, how do I get a bigger N? Do I divide by a bigger number or a smaller number? And you could do the math. You know what? Let's just quickly do the math. It's not that hard to do. If we rearrange this equation for V, V is going to equal C over N. Just some quick algebra. Kick the V to the other side, divide by N. So V in H2O will equal 3e to the 8 divided by 1.33. V in glass is going to equal 3e to the 8 divided by 1.5, and you can already see that when you divide by a bigger number, you get a smaller number. But you can do the whole process just to prove that to yourself. So in glass, it is going to be 2 times 10 to the, mine didn't do scientific, so 1, 2, 3, 4, 5, 6, 7, 8, 9. No, 3e to the 8. I miscounted. 3e to the 8. Oh, and this is a good point as well. 3e to the 8 divided by 1.33. 2.25 times 10 to the 8. And so looking at these, yes, we see that it travels faster in water. That is a bigger number than the bottom one. 2.25 is a bigger number. All right, couple things to take away from this problem. Bigger the N, slower the wave. Super easy problem for me to ask for the test. Super easy. Bigger the N, slower the V. You can see that from the math here. Other thing to point out is you can check your work really easy. The beautiful thing about light problems is if you're ever solving for velocity and you get a velocity bigger than the speed of light, you did something wrong. It is impossible to go faster than 3 times 10 to the 8. So if you get a number bigger than 3 times 10 to the 8, either you broke the rules of physics and you discovered faster than light travel, which kudos to you, but more likely you made a math mistake. So, always a good check if you're solving any problem ever that has to do with speed. If you ever get a speed bigger than the speed of light, you messed up. Good thing to keep somewhere in your mind. All right, here's a table that's really hard to read of various index of refractions. You do not need to have these memorized. You do not need to have these written down. I will always give you the value of N in a problem. Or I'll say solve for N. You do not need to know the index of refractions of various materials. I just wanted to show them to you because they're kind of interesting to talk about. Air, very close to 1. Light travels very close to the same speed as it does in vacuum and air. Makes sense. Air's not made of very much. All the gases, basically the same thing applies. The speed is very close to the speed that it would be in vacuum. Now, as you go down the list, benzene, those are some liquids, and so gets angry when I zoom in. Benzene, carbon disulfide, ethanol, water fresh. Those are all, around 1.5, 1.3. They're liquids, not as dense. When you get to the solids, all the solids are bigger. Diamond is quite dense, and it also has to do with the crystalline structure. It's not just density. There's a little bit more involved. But that's a general kind of rule of thumb. But you do see an interesting thing here where ice has a lower index of refraction than water, meaning it travels faster in ice than it does in water because ice is less dense than water, so you do get to see that there, which is kind of cool. This isn't cubic zirconium, I don't know what this is. Some kind of zirconium is a little bit less dense, a little bit less crystalline than diamond, whatever. So on and so forth. I will give this to you in a problem. All right. This is the last equation before I quote. Let me see if I do total internal reflection. Okay, I do, but that comes from this equation. This is the last equation. Any other equation that we're going to see in the slides is just a modification of this. There is one more, but it's just a modification of this equation. It's very specific case. Snell's law. What a name, right? How would you like to have a name that's real close to snail? I don't know, I don't know his background in other countries. One of the nature of name. If it was an English name, then that's unfortunate. If it's another country, it totally makes sense. It is what it is. You don't get to choose your name. I only said the last one. N1 sine theta 1 equals N2 sine theta 2. This equation, I will label the things on here. N1 is medium 1. It's the index of refraction for where you start. N2 is the index of refraction for the material you enter. Theta 1 is the angle you enter with. Theta 2 is the angle you exit with. These are measured with respect to the normal. That area vector. That's the area vector there. That's the area vector there. Just like reflection. And light comes in, hits that, and then comes out. And it bends. Mathematically, if you try this problem, there's basically some quick rules you can see, which is that light bends towards the normal when traveling to a denser medium, and light bends away from the normal when traveling to less dense mediums. Basically, the problem below this is just which direction you're going. You all can see here, medium 1. And this problem down here, N1 is less than N2. And you can see that the angle that it exits with is smaller than the angle it enters with. You do not need to know this. You can always find this with the math. You can make up some numbers, make an N that's big, make an N2 that's small, make up an incident angle, and prove this to yourself. Or you can just have this kind of written down. It's very easy to derive. Make N1, make N2 1.5, make the incident angle, who cares? And then solve for the exit angle, and you'll see that the exit angle is smaller. But this equation describes how light bends, and it's such a simple equation, which is kind of cool. Like, all this complex stuff that's happening. Why is light even bending? Because it's slowing down, and all this, it comes into such a simple, elegant equation. It's always nice when stuff like that happens. You have this complex stuff that's going on under the hood. Like, why does it slow down? That's a really complex question. How much does it slow down by? Whatever, all that stuff. You're just going to have this and it's easy peasy. Those index of refractions, those are pretty much all measured experimentally. They are not, theoretically, that would be a nightmare, I'm fairly certain to calculate. Those index of refractions are just done from really careful experiments because there's so many complex things going on here. All right. There you go, light bends. There's lots of examples of this. You can look around, look in water, all that kind of stuff. All right. I'm going to start this one. I'm going to let you all try it. Because this one's, I haven't quite done the math through this. I will actually leave this open as I'm solving the problem. So try it, try to get the answer, but I will actually show how to solve it and then also let you fix your answer for this because it is a little bit more involved. It's not just conceptual. This is math. There's no escape. You have to get out a calculator unless you can do sine inverse in your head. I can't do sine inverse in my head. So it enters at a 60-degree angle, and it's starting, so it says, what is the angle that light would enter water? And I'll draw a picture for you all as well. So it says it's would enter water from air. So it's starting in air, because the wording here I'm not the biggest fan of. It enters at a 60-degree angle. It's asking what the exit angle is. It enters with a 60-degree angle. That's pretty clear. It says it entered at a 60-degree angle. I can't really make that much more clear. It enters with a 60-degree angle. What angle is it going to exit with? And I won't draw that one, because that may give away some of the answer if I draw it correctly. But there's my incident angle. That's the angle it enters with. 60 degrees. Make certain your calculator is in degree mode, not radian mode, unless you want to convert to radians in your head. That's always something to be careful of. We pretty much always want to be in degree mode in this class. So at 3 minutes, I'll start working through the problem. All right, so if you're still working on it, that's perfectly fine. I'm just going to start working through it up here as well. I'm going to leave it open. So if you did get it wrong, you can always change your answer. So I'm actually very encouraged with the answers I'm seeing. My N1 is that incident, what I'm starting in. So I'm starting in air, 1.0003. I'm ending in water, 1.33. And my incident angle is at 60 degrees. I am solving for the exit angle, and what did I call that in my picture up here? So I'm consistent. Snell's law, I called it theta 1, theta 2, so I will actually call this theta 1, and I'll call theta 2 equals mystery. Equation is N1 sine theta 1 equals N2 sine theta 2. The numbers go with each other nicely. N1, what you start with, the angle you start with. N2, what you end with, the angle you end with. And then when we plug and chug, I'm going to give myself some room here. Actually, I'm going to do some algebra. We're solving for theta 2. So I will actually write the steps. So I'm going to divide the N2 over. So sine of theta 2 equals N1 sine of theta 1 divided by N2. All I did was divide the N2 over. Nothing crazy there, nothing fancy. And I wrote it in terms of sine theta 2. I moved that just to make it easier to see. Anyway, what's the opposite of sine? Sine inverse. So theta 2 is going to equal sine inverse. Make certain you know where that is in your calculator. It's generally above sine. You hit that second function. First time we're using sine, maybe we've used cosine inverse before actually. That may show up in a problem or two. Sine inverse of 1.0003. It doesn't change the answer that much to put all those decimals, but might as well. Sine of 60 divided by 1.33. You plug that into your calculator and you get 40.64 degrees. Which, so there you go, you can change your answer. You got a handful of seconds. We'll go to 5:30. Which is smaller than 60. When you're going from a less dense medium, a small n to a big N, your angle gets smaller. If you go from a big N to a small n, your angle gets bigger. So, small to big, gets smaller. Big to small, gets bigger. There you go. Great. Good job, everyone. Can't even mark the right answer while it's still going. All right. Fantastic. Wow, so many of us got it right. So good. Fairly straightforward, classic plug and chug kind of problem. There's not really much fanciness here. The only thing you have to do is know which one's N1, which one's N2. That's the only mistake I expect people to make if they make a mistake on this. N1's what you start with, N2's what you end with. All right, last thing that we need to cover, this is just an extension of this. The question is, what is the maximum angle theta can reach, and what effect does this have? The key to this is we have to be going from a dense material to a less, we need to go from a big N to a small N. I just told you all that the angle gets bigger when you go from a big N to a small N. There's a limit to how big the angle can get. It's 90 degrees. So, go ahead and try solving this problem, y'all. I'm going to draw the picture for it. Light is leaving water and going into air. So this one, now that I've shown you how to do it, I'll let y'all do it, but I will draw the picture. So let's still make water on the bottom and air on top because that makes more sense to me. That way we don't have water floating. If I have light coming in, here's my H2O, with some angle, doesn't say what, it says what is the incident angle? What is the angle it's coming in with? Such that the exit angle is 90 degrees, right along that surface. What is that incident angle? Because as I mentioned, at some point, if the angle gets bigger and bigger, there is some angle on the bottom such that the angle will end up being 90 degrees. And that is the maximum angle we can reach. You go any more than that, and we'll see what happens. That's the max amount that light can bend when it exits. My answer, my rounding is off on the second decimal place by a tiny amount. But there's only one answer that's that close to it, so I realized why I did that. It's not a huge deal. But as always, y'all, if there's ever any rounding, and you just pick, I would never pick an answer that's drastically off. That would be off by any kind of rounding. All right, we'll go to 310, and I'll start solving this. This one I will close, since I showed you how to do the first one. 5, 4, 3, 2, 1. So, here's the fun thing. We can basically use the exact same setup as we did as the last problem. You can still call this N1, in which case this is theta 1. You can call this theta 2, in which case this is N2. And then the problem is almost identical to the last one we did, except now N1's theta 1 is 90 instead of 60. So last time we showed that, so we had N1 sine theta 1 equals N2 sine theta 2. We solved for theta 2, which is exactly what we're doing here, and it was sine inverse of N1 sine of theta 1 over N2. It's the exact same equation. You just plug in 90 degrees instead of 60 degrees. You plug all that in, and you're going to get an angle of, and when I did this, I used 1 instead of 1.0003. So technically, if you use that 1.003, the answer should be 0.77. None of them are any close to that. This is called, let me give you all, there you go, good job, woohoo. This is called the critical angle. This is when total internal reflection occurs. The words describe what's happening. No longer will it pass through at all. If the light hits with this angle or bigger, the light will not exit the material. You all can experience this for yourself if you're swimming in a pool and the water surface on top is pretty clear. If you look at the surface, like pretty smooth, if you look up at the surface, there will be an angle at which you could no longer see the sky. And you're seeing a reflection of the bottom of the pool. There's an angle at which you look at, if you're going from a dense medium to a less dense medium, at some point you all can see what's going on here. As the angle gets bigger, that incident angle, this reflected angle goes down and down and down. At some point it hits this and it can't go any lower, at which point the light doesn't pass through at all. So, this equation right here is just that's what we plugged into the last thing. Yeah, this may not look the same. Let me show you all that this equation is the exact same that the one that you all just wrote down. So in the last slide, I wrote theta 2 equals sine inverse of n1 sine theta 1 over n2. And you look at this and be like, where did sine of theta 1 go? Theta 2 equals sine inverse. We had n1 sine theta 1 over n2. If I just plug in, and it doesn't matter which one's 1 and 2, just be consistent. If you want 1 to be water, make it water. If you want 1 to be air, make it air. Just make certain your angles go with the right ones. Doesn't matter which is which, as long as you're consistent in terms of that. And then we said n1 sine of 90. Sine of 90 equals 1. So it disappears. Sine of 90 is 1, so you get you get n2 over n1. Okay? So if you're wondering where that sine of 90, that sine of theta went, well, we plugged in 90. Sine of 90 is 1. There you go. So that's the angle at which it happens. Why is this relevant to you all? This happens all the time. We use this for fiber optic cables. Fiber optic cables are glass, and then the material around them has a lower index of refraction, such that the light hits at an angle where it always bounces. This is why you can bend a fiber optic cable and it still works. Because the light always is just bouncing inside it and propagating along, and it's so fast because it's light. Light's a heck of a lot faster than electrons. So, just kind of fun facts for you all. All right, we have 5 minutes. I will solve one of these, and the other I'll just post a solution. They're both fairly straightforward. I'll do. Sure, we'll do this one. This looks more involved. But they're neither one are bad. I'll post a solution to the other one as well. You can determine the index of refraction of a substance by determining its critical angle. What is the index of refraction of a substance that has a critical angle of 68.4 degrees when submerged in water? What is the substance based on the table below? That's where you have to go back to the other table. And your all's problem set, I give you the table, it's in there. So, what would be the critical angle for the substance in air? So, what's given? Critical angle equals 68.4 degrees. In this case, when submerged in water, so this means theta critical is going to be, and we'll start using this notation here. We'll use the N2 is the one it's exiting into. So N2 equals 1.33. That's the material it's going into. And that's all we're given. All right, step 2, what are we solving for? We are solving for N1. We're solving for the material that we're starting from. Our equation is theta critical equals sine inverse of N2 over N1. Let's rearrange and solve for N1. So N2 over N1 equals sine. The opposite of sine inverse is sine. And to get N1, divide the sine over. I'll let you all see the algebra for yourself. You can come back and check how the heck I did that algebra. N1 was on the bottom. Kick it over, divide the sine over. Nothing crazy. Step 4, N1 equals 1.33 divided by sine of 68.4. So this problem is just using the equation and some little bit of algebra to rearrange it. So nothing too crazy, but do make certain that you can go back and know how to do this algebra. That's the only challenge here in labeling things appropriately. All right, we should be able to check our work. We should be able to recognize that for total internal reflection, we have to be going from a more dense medium to a less dense medium. So if our final is 1.33, we better get an answer that's bigger than that. That's the way you can check your work when it comes to these. Whatever you start in needs to be bigger than what you end in. My number is bigger than what I ended in, so that's a good sign. Yay me. All right, what is that substance based on the table below? You can have a pretty good guess that I'm not going to give you a problem where I ask that in the test, because a table takes up a lot of space, and I'm not going to want to use a bunch of space to put a table, but this is interesting on the problem set. If we go down, and this is the table I give you in the problem set. It's the same one in the slides. I look for 1.43. Scroll. Oh, look, fluoride. There you go. And this is literally something that they do to determine what materials. This is a way of characterizing materials. Shine a laser from one to the other, determine the critical angle. If you know it's all made of one thing, this is a way to characterize materials. Every material has a specific index of refraction. The critical angle would change. I'm not going to bother with the last step because we don't have time. I will post that later. Nothing too fancy. These problems, in my opinion, aren't that bad. You can decide that for yourself, but compared to everything else we've done in this class, this is just plug and chug, basically. Not really combining much, just equation, numbers, algebra, solve. So, anyway, all right, there you go, y'all. If you have any questions, feel free to come on up. Again, I will post the solutions to, I will work out this one as well, and I'll post it. But nothing too crazy here, y'all. I'm not going to give you any crazy curveballs or anything. The problems